Okay, so let's have a look at this cubic function. Okay, x to the power of 3 plus 3x squared minus 9x minus 27. One thing we know that's very easy is the constant, the same as with a parabola and a straight line. The constant value gives you a y-intercept. So at least when you look at this, you know that will be at negative 27. Okay. But now what we're going to look at is the derivative of this, which is going to be the derivative 3x squared, 2 times 3 is 6x minus 9. And now this derivative makes a parabola. So we're going to look at this parabola now. If you think of a parabola and you want to sketch this, you can say, if I put it equal to 0, remember when you put the parabola equal to 0, you can find your x-intercepts. Okay? Okay, so now, when you get your x-intercepts, when you solve this, you get your x-intercept negative 3 and 1, you will see that negative 3 and 1 is the x-intercepts, negative 3 and 1, but it's also the negative 3 and 1, which is your x-intercepts for the parabola, is also your turning points for the cubic function. Because remember, when you put the derivative equal to 0, you find your stationary points. Okay, so that's something to keep in mind. A parabola's x-intercepts is the same as the cubic function's turning points. Okay, and then what else do we know? We know that this parabola has a y-intercept of negative 9, and obviously at negative 1 is the center. So we can actually say the parabola is going to look something like this. Something like this. Okay, we can just make one. It's a little bit more this way. So it's going to look something like this. Where the x-intercept is the turning point, the x-intercept there is the turning point. And then the other important thing is the turning point of the parabola, okay, is called the point of inflection of the cubic function. That's also important. The turning point of the parabola is the point of inflection of the cubic function. And the point of inflection is where it turns from concave up to concave down, or from concave down to concave up. And that's when you look at the double derivative. Okay? So if you look at the double derivative here, we said the derivative is this. So the double derivative would be 6 equal to 6x plus 6. Okay? When you put the double derivative equal to 0, when you put 6x plus 6 equal to 0, and you solve it, take the 6 over its negative 6 divided by 6, you get negative 1. Then that negative 1 is your point of inflection. So there, at negative 1, you got your point of inflection. So that's how we use a double derivative. We put the double derivative equal to 0, we solve x, and the value we get is called the point of inflection. That point is the point of inflection. And that's where the graph, the cubic function, changes either from concave up to concave down, or from concave down. In this case, it's concave down up to there, and then it's concave up to there. And that means the concave down and concave up. It means that when the derivative, the double derivative, let me just do that part quickly. When the double derivative is smaller than 0. So if you put the double derivative smaller than 0 and you solve it, let's see, 6x plus 6 smaller than 0, you get 6x smaller than negative 6, x smaller than negative 1. So when the double derivative is smaller than 0, it's concave down. Okay? So if you want to know where is the cubic function concave down, you have to put the double derivative smaller than 0. If you want to know where's the cubic function concave up, you have to put the double derivative bigger than 0. So you can see x, sometimes they just ask that, for which values of x is the cubic function concave down. And then you have to put the double derivative smaller than 0, and you solve it. If they say where is the cubic function concave up, you put the double derivative bigger than 0, and you solve it. So concave down is actually, you can say, it's where it's losing speed. Like this graph, if you think of it as a roller coaster, it's going slower, 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 slower. Now it is kind of picking up speed here again, but this part is where it's really going big. Now it's going faster. You see, now it starts going faster, and then it starts going slower again. So this part here is where the graph is concave up. Concave up. And this part here up to there. This part here is where the graph is concave down. Another way to test it, this is the last way to test it, is when the tangent is above the graph. If my tangent is above the graph, then it's always concave down. If the tangent is below the graph, it's concave up. So if you take a ruler and you put it on the graph and it's below the graph, then you know this part is concave up. But if the ruler is above the graph, see up to there it's above the graph, then it's concave down. At the moment it starts going below the graph, the tangent, you know it changes from concave down to concave up. Okay, so that's a question on its own sometimes. Where is the graph concave up and where is the graph concave down?